No. So that's actually a hint. As soon as you saw y squared, which is an even power of y greater than 1, you go, not going to be a function. It's not going to happen. And, oh, this one here. I kind of can't remember. I think I remember this one. It is x, oops, I'm in highlighter. X squared minus 2x plus 2xy plus y squared equals 1. So knowing that crazy rule again, is it a function? I got y squared. That's an even power of y greater than 1 function. I'm already thinking no. But I could actually algebraically be more specific. This is a factored look at that 2xy means I'm talking x plus y, quantity squared, equals 1. This is the issue. As soon as I introduce solving this, dude, square root both sides, square root, and I see a square root introduced to my graph, and that means I need a plus or minus 1. And that right there tells you that for a given x, you're actually going to do, once you're going to do plus 1, another one you're going to do minus 1, you're going to have 2 outputs. That's not fun. So y equals plus or minus 1 minus x. This gives you 2 results for every single x you put in there. That's no fun. You ready, team? You holding on? Holding in? It's a lot. It's a lot to think about. Hopefully a little bit of review. We're getting close. I'm going to turn the page. You have to squawk if you want me to come back. So let's close out 1.4, and then we'll get to parametrics, which are actually fun because we can play with our calculators. Closing out 1.4, home stretch. If I say, is the ordered pair in the relation, I mean, does the ordered pair satisfy the relation? Like, does it work? Do you get a real result? So I think for the first one, we'll call it A and B and C. So part A, if I put in x is 2, that means 2 squared. Y is negative 5 plus y squared, and that's 5. Is it? So the question, big question mark, is that 5? This is negative 20 plus negative 5 squared is 25. Yeah. Yes. It works. I get 5. Total yes. Works. B. Does 1 squared times 3 plus 3 squared equal 5? That's 3 plus 9. No way. So we'll highlight in the no color. That's the no color. No! It's not a function. C. 2 squared times 1 plus 2 squared equals 5. I got, what? Did I put the wrong number somewhere? Is it 1 squared? Oh, that's what you said. Can I erase that? Oops. 1 squared. 4 plus 1 is 5. Bingo. That's the yes color going in yellow for yes. Good. That's the key. Snap. As domain. Range. I'm asking for both. My challenge to you, why don't you take the next, can I pause my recording? Do I have to make a new one? I don't really want to make a new one. I guess I have to make a new one if I stop. That's okay. Let's do it. Let's do it together. You just help me. Please help me. Please. Domain. Number 1, if you guys want to do domain, you just look at these. All right, let's count them. Remember 9, we have a record of 8, right?
It tells you at the top.
1, 2, 3. Oh, it does?
Yeah.
Oh. Okay, thanks. There are not a lot of things I get to look forward to every day, Nick. Domain, dividing by 0 is a no-no. I see that -4 would cause that. So I hope you got negative infinity of 4 union 4 to infinity because of the vertical asymptote at -4. And I mean to put negative, not 4. Just write that, yeah. Vertical asymptote, x equals -4. That's just interesting information. That's the domain. So let's do domains all the way down. Domain of radical x plus 1. Oh, we know that. We did it like 5 times. -1 to 0, -1 to infinity, I'm sorry. Because I can't have anything less than -1 because I get a negative in my radical. Number 3, most of us go, oh, it's just -1 to infinity with a bracket again at number 3 because of the radical x plus 1. But, oh no. You can't put in -1 because if I put -1 in this thing right here, -1, I get 0 and you can't divide by 0. No. So you need a parenthesis -1 to infinity. That comes from solving that whole denominator set equal to 0. You'd find that if you very carefully went in there and said, radical x plus 1 can't be 0, square both sides, subtract 1. You'd see it. It'd jump out at you. Next, log. Little graph of log. Log is a graph we did yesterday, one of our dirty dozen. Looks like that. It's got a domain. It's a restricted domain. It's always greater than 0. And you know why that's cool with radicals? Because radicals require that anyway. So the domain on this one is just the log is always bigger than, the x is always bigger than 0. But only, that's a misnomer. The x's of log of x are always bigger than 0. But what I need is like log x itself. I need to find out when log x itself is greater than or equal to 0. And do you remember yesterday I said there's a really key point? When does log of x become bigger than 0? Remember that location right there? 1. Thank you, Abe. It does happen at 1. So our domain on this one starts at 1. You can put in 1 and get 0. It's okay. Including 1 to infinity. No. Next one, f of x equals 4. Sydney, your $1 million question on this. That's a horizontal line. You know, the graph is at 4. That has a domain of all real numbers. Its range is really interesting. So let's start doing ranges on the way up. The range of that one is actually just 4. That vertically, that's the only output you ever get on number 5 there. So I'm going to put a green banner across here saying I'm done with 5. Got its domain and range. 4. Let's get the range on 4. If I do log of x, radical log of x, and the first x I put in there is 1, and it gives me 0, and then the next number I put in maybe is, I don't know, something bigger than 1, I get something a little bit bigger than 0, you'll find that this whole graph, it starts at a height of 0. You can get 0 for this function, and it climbs up. You can also graph it, and you can also look at that and enjoy it. It's beautiful. But the graph of radical log of x starts at a height of 0 at x equals 1, and then continues to ascend from there. So the range is 0 to infinity. Weird. You might have to graph it to see it, but it's a good one to know. You can get 0 as an output. You can also get anything bigger than that. And please, refute, find stuff, fight. Do you want to see the graph of that one? I'm curious. Should we graph radical x? Shall we graph that? Let's roll. Here Here comes TI graph. Come on, TI grapher. Move real fast. Why is there so much stuff open? There. It's coming. Here it goes. While we're doing that, let me pick on the one above it. The range on the 1 over radical x plus 1. That's kind of a cool graph. We need to find out what's taking place on that particular graph. So we will here momentarily. So I think we should graph a lot of these. Yeah. The TI Smart View, it means that we're going to see a TI calculator, and it's the smart view of it. It's an online calculator. It's my calculator that I can use up here so you guys can see it. That's just the name of it. So TI Smart View brings us this function. I'm going to go radical. We're going to put log of x in there. I'm going to use natural log of x because that is my favorite kind of log. You guys can find it right here, ln. It means log base e. Logs can have any base you want. Log base e is our favorite, ln of e. And then I put x in there, just like you'd expect. Close it out. I'm going to do zoom 6 because that sounds good to me. There it is. See? 0 to infinity, just like promised. Number 3, not so easy to figure out. Go for it, Abe.
What's the difference between natural log and log?
Oh, okay. So natural log and log. Let me default to my big screen so everybody can see it and it's in recording. Natural log of x is actually log base e of x is the same thing as ln of x. It's shorthand for it. And any other log, somebody has to specify what the base is. You can have log base 2 of x. We could graph it as a function. And there's a lot more to it. And let me tell you, we spend a lot of time on logs because it's kind of a difficult topic. But log is the inverse of exponents. So if I say y equals 2 to the x of an exponential like that, I would say as an inverse to that, I'd say log base 2 of y equals x. So they're inverse functions of each other. Weird, huh? But that's where it comes from. They literally mean like they just undo each other. One goes one way, one goes the other. When we graph them, they're inverses of each other and so on. So we'll get more into that, but that's to help you satiate that for a moment. Now, to the grapher, y equals enter. I don't want to graph that log thing anymore, but I do want to take a look at 1 over radical x plus 1. This graph is mysterious, to say the least. I want you to tell me what you think the range is. I think some of you could benefit from a piece of gum for a number of reasons. But one of them is, I'm going to get a piece, but I'm happy to offer to you if you can correctly tell me the range of this function. That's domain.
3 to -3.
Vertically, range is up and down. So what's the lowest that graph can be? Let me at least help you with the low. Okay, it looks like it starts at 0. You'd be safe to say it goes from 0 to 3, 4. Looks like I'm the only one chewing gum today so far.
7. 0.07.
Zoom in. Close. Yep. If you multiply it by a lot. Check this out. If I zoom in, now look, right in the middle of my graph, I should be right at the tip of this, right after I zoom in. What? This is weird. Where's that going? Should I open my window up?